Yes, welcome to this session on material science and engineering subject. So, in today's lecture, we will learn. In today's lecture, we will learn engineering applications of eutectoid steel, hypoeutectoid steel, and hypereutectoid steel. Okay, so in previous lectures we have learned about different microstructure evolution at different regions, such as on eutectoid point, hypoeutectoid point, and hypereutectoid point. We have seen in eutectoid point, below eutectoid point, we get a lamella of cementite and alpha iron. We called it perlite, and in hypoeutectoid region we got the region of alpha dash, that was proeutectoid ferrite, and a region of perlite, that was the combination of ferrite and cementite. Okay, and in hypereutectoid steel we obtained the proeutectoid cementite and the region of perlite, that is alpha plus cementite Fe3C. Now, one basic question comes into our mind, that we have drawn a colorful diagram of these different phases, or the colorful diagram of the microstructures. Okay, so what do we understand? What do we understand from microstructure? Okay, now this question comes into our mind, right? So let's try to explore what is the uh, what is the properties, what are the properties corresponding to each microstructure. Okay, fine. So just before starting this lecture, I am again drawing the eutectoid steel diagram. So this is one line, and this point we have taken as eutectoid point, and this temperature is 725 degrees Celsius. This is temperature in degrees Celsius. This point is 910 degrees Celsius. Okay, and we draw one line like this to this. Okay, and here we have gamma phase, here we have alpha phase. Okay, and here we have cementite phase. Okay, so can you tell me what will be here? Alpha plus gamma, here gamma plus Fe3C, here alpha plus Fe3C, and this on x-axis we have carbon weight percent. So this point maximum was 6.67 weight percent of carbon. This is 0.8 weight percent, and this point is 0.02 weight percentage of carbon. Okay, now let's try to see what is the meaning of, what is the properties of, in terms of engineering applications. We means that in what is the meaning of engineering applications, that is how these materials are used in the industries, okay, in different industries. So we will assign a specific material depending on the requirement in the industry, okay. So it is very important, it is essential to understand the material property of each phases. So in terms of material property, we are more concerned about the mechanical properties, okay. So now let's try to explore. So first phase which we have, this is ferrite. What happened to this? So first phase which we have encountered with, this is ferrite or denoted by alpha, okay. So now let's try to understand what is the mechanical properties corresponding to this alpha phase. So this is a soft ductile, this is ductile in nature, and it is having magnetic phase, it is magnetic, okay, and this is having BCC structure, okay. And in alpha ferrite you can see from this diagram what we get as observation, very low solubility of carbon, okay. So you can see that maximum it consists 0.02 weight% of carbon at 725 degrees Celsius. Okay, so this is what maximum we will get this point of carbon solubility at which temperature 725 degrees Celsius. Now let's try to understand another phase which is austenite. This is denoted by gamma. This is phase 2, okay. So austenite is a softer, this is softer, this is more ductile, okay, more ductile than alpha ferrite, and this is non-magnetic, and this is having FCC structure, okay. Now one important point regarding this, you can see in cementite we have very higher solubility of carbon up to 0.8 weight% for eutectoid steel, okay. But when we observe the complete iron carbon diagram, we will get it is having carbon percentage in austenite, it is around 2.1 weight percentage at 1150 degrees Celsius, okay. So you can refer to your diagram which we have discussed in previous lecture. So the observation is can dissolve more carbon. Okay, this is up to maximum up to 2.1 weight percent of carbon at 1150 degrees Celsius. Okay, and one important point that this is the phase into which steel is heated for heat treatment. We will explore this point in further lectures. This is called austenitizing. Right? So their austenite will be the starting phase, and from here the heat treatment of steel starts. Right? So we will discuss this point in I think next lecture. Okay, so and third phase is cementite. This is what Fe3C. Cementite Fe3C. So this cementite is very hard phase. So if it is hard, this will be what here? This will be brittle in nature. Okay, and this is what having magnetic properties, and this also form intermetallic properties. It is having intermetallic property because this is what formation of metal, and this is carbon is non-metal, so it will form one intermetallic compound. Okay, and in this carbon, if you see this cementite, so here, so this cementite contains maximum of 6.67 weight percent of carbon. Okay, so this you can see, this is the maximum solubility of carbon in cementite. Okay, and in alpha ferrite and cementite, as we have discussed, these carbon atoms sits inside the tetrahedral voids and octahedral voids present in the BCC or FCC crystal structures. Okay, so these are the points which are very important for understanding or selecting the specific material for specific engineering application. So the question is, which steel we have to select, which steel we want to select. You want steel present in this region, you want steel present in this region, that is eutectoid, or you want steel present in this region. Okay, so this is our question, how to select a specific steel for a specific engineering applications, right? So now let's try to explore it more in next slide. So let us begin with hypoeutectoid steel. Let us begin with hypoeutectoid steel. Hypoeutectoid steel. Okay, and another is eutectoid steel and another is hypereutectoid steel. Okay, so let me erase this so that we have a nice space for writing. Okay, so now let's see how we classify this. So we have explore it earlier also. So here carbon content, if we see carbon content, okay, so here carbon content is less than 0.8 weight% of carbon. Okay, now let's see what is the microstructure. What is its microstructure? So you can refer to previous lecture or from your notes that upon slow cooling we will get proeutectoid ferrite plus perlite. Okay, now let's explore it more. So how it looks like if I draw the hypoeutectoid steel microstructure, as we have already discussed in our previous lecture. So this was something like this. Okay, and this phase was how we have denoted it. This is proeutectoid ferrite. Okay, and in remaining regions we obtain the perlite. This is what alternate layers of alpha ferrite and cementite. I think I am choosing a different color for just for representation. Okay, now let's take another phase with this. Okay, so this is what perlite. It is combination of alpha ferrite and cementite. Now let's discuss its mechanical property. Now mechanical properties. So the first point is strength. So the strength of this phase is low to medium depending on the carbon concentration. Depending on the carbon concentration. So what is happening here? As we increase the carbon percentage, as we increase the carbon percentage, strength will increase. Okay, so you can see that if carbon percentage will increase, the strength will increase. And on increasing the carbon concentration, the proportion of hard perlite increases. Okay, and let's discuss its what happens on ductility and toughness. This is one property, strength. Next property is ductility or toughness. So ductility and toughness is high. Okay, so the funda is, so you can see here the continuous network of, you can see here, this is ferrite in is soft in nature. Okay, so what will be happen, this is soft when there is a compression on this phase, so this ferrite phase will deform properly and it will go and it will undergo a high plastic strain or high plastic deformation. So these materials are highly useful for the energy absorption applications. Okay, so the continuous network of soft perlite, soft ferrite. So you can see this region is soft ferrite. Soft ferrite, or you can see we have denoted it by alpha dash. Okay, the continuous network of soft ferrites allows for significant plastic deformation. Okay, and so this phase will be very high energy absorption capabilities. Okay, now another mechanical property, very important mechanical property, is hardness. So here hardness is low to medium. Hardness generally depends on the carbon concentration, that how much carbon has located, how much carbon is situated inside the interstitial voids, which we have discussed, that was octahedral and tetrahedral. Okay, so as here carbon concentration is very less, so hardness will be low to medium. Okay, now let's explore for what is happening in eutectoid steel. Okay, so let me draw one lung. Okay, so discuss with you let's discuss the eutectoid steel. So in eutectoid steel, this carbon content is, so the carbon content is around 0.8 weight percent of carbon in iron matrix. Okay, now let's see how does its microstructure looks like. So its microstructure, upon slow cooling, we will get what 100%, we will get 100% perlite. Right, now let's try to draw the microstructure for eutectoid steel. So we have learned it in our earlier class. So let me draw it properly. So this is, we will get an alternate layer of ferrite and cementite. Okay, so this is the microstructure of eutectoid steel. Okay, so what is perlite? It is like mother pearl, which is nacre. And what is nacre? In nacre, if you search it on Google, nacre microstructure, there you will get a combination of hard and soft phase. Okay, so here hard phase is cementite and soft phase is what? Alpha ferrite. So this magenta color represent alpha ferrite region. Okay, So this is this magenta color I am representing alpha phase, and this red color I am representing Fe3C. So we have learned earlier that alpha ferrite is a soft and ductile phase, okay, and cementite Fe3C phase, this is very hard and brittle, okay. So perlite is what it is. This phase is having combination of soft and harder phase, okay. So let's try to explore its mechanical property. So first we will have strength. So strength will be high. Right, because perlite itself is a very strong micro constituents, okay. So this is because it hard and soft phase, this generates a very high tensile strength or compression strength inside the material, okay. Now let's explore what it stands for. Ductility. So ductility or toughness is moderate here, okay. So it is less ductile than hypoeutectoid steel, okay, due to the absence of this due to absence of free ferrite, okay. So this is it is having moderate toughness, okay. So I think video got stopped. So you can see in eutectoid steel we have discussed that carbon concentration is 0.8 weight percentage of carbon, and it is having 100% perlite in nature. And in this microstructure we will get alternate layer of alpha ferrite and cementite, right. Now in mechanical property we have learned that its strength is high because it is having perlite phase, and perlite itself is a very strong microconstituents, okay. And it is having moderate ductility and toughness. It is having moderate ductility and toughness. It is less ductile than hypoeutectoid steel. Hypoeutectoid steel, okay, because here we will get absence of proeutectoid ferrite, that is alpha dash. Proeutectic ferrite, it is very soft and ductile, so here it is absence, so it is moderate ductile, and it is less ductile than hypoeutectoid steel, and its hardness is high, okay. So first we are understanding here what is the mechanical properties in terms of strength, ductility, toughness and hardness, okay. Then after this we will explore that what should be the engineering applications or industrial applications of different types of steel, that is hypoeutectoid steel, eutectoid steel and hypereutectoid steel, okay. Now let's come to hypereutectoid steel. In hypereutectoid steel, carbon content is greater than 0.8 weight percent of carbon, okay. And this is, if you see your diagram, the first diagram of iron carbon diagram, so we will have a limited maximum concentration, okay. So the concept is this is greater than 0.8 weight percentage, but generally it is kept up to 1.5 weight percent. So typically up to 1.5 weight percent of carbon, okay, it, for tool steel, okay, and beyond this brittleness becomes excessive. Okay, so what is going to happen if the carbon concentration is beyond 1.5 weight percentage? So it it will going to deteriorate the mechanical properties, okay, and the overall structure will become very brittle in nature. Okay, so now let's, what is the microstructure during slow cooling? Okay, so here we will get, so in hypereutectoid steel we will get proeutectoid, proeutectoid cementite plus perlite. Okay, now let's see how does it looks like. So we have already drawn it in our previous lecture, but I am again drawing it for more clarity. Oh, so here we have this reason. If you see the Uttar Pradesh Sarkar government logo, you will get this type of microstructure there also. That is the Trivedi Sangam from Prayagraj, Ganga Yamuna and Saraswati combination. Okay, fine. So let's try to explore it. So here we have so let me cementite I am writing with red color, so let me draw it with different colors. So this is what proeutectoid cementite. What is the meaning of proeutectoid cementite? That this phase has formed just before the eutectoid point. Okay, so this is one phase. Now let's draw another phases. Okay, so we will get alternate layer of this ferrite and cementite, that is called as perlite. So this magenta color I am denoting for alpha ferrite, and this will be for cementite. So cementite is very hard phase. Okay, so this is what pro-eutectoid cementite, and this is what perlite. Okay, so this is the microstructure. So this phase is reddish, is for Fe3C, and this phase is for alpha ferrite, and the combination of this will make perlite. Okay, so now let's explore its mechanical property. Okay, so here if we see about strength is very high. Strength is very high. And why this strength is very high? So we know that here cementite phase is present, so that's why its strength will increase. The presence of hard cementite increases the hardness and strength. Okay, now if this strength is very high and carbon is because of this cementite phase. Okay, now let's try to see what is happening for ductility or toughness. Okay, I'm not writing this, it is already written on the left side. So ductility and toughness is low. Okay, so now you can think why ductility or toughness is low. That you can see the continuous brittle network of this pro-eutectoid cementite. So this pro-eutectoid cementite network is very brittle in nature, and if during tensile or compression loading, if any crack generate, then this crack will propagate along this network, and the material will fracture very early. Okay, so let me write it properly. The continuous brittle network of cementite make the steel prone to crack propagation. Okay, so for this reason, what we have to do, these hypereutectoid steel are often heat treated to spheroidize the cementite, and which improves the toughness. Okay, so what we do its heat treatment to spheroidize the cementite. We will explore this section in later classes. Spheroidize the cementite phase, and hence toughness will improve. Okay, so here by spheroidizing, the toughness or ductility will improve. Okay, so these are the different property, and hardness is very high. Okay, now you can think if the hardness is very high, what do you understand by hardness? Hardness is a surface phenomena, right? We have done a lot of experiment in our lab, that we took a indenter which have a typical ball sized uh, tip, and we indent on the surface, right? Now can you tell me, if I am using any component, okay, and we want that it should not get, that we want that its hardness should be high, okay, so what will be happen? It's indented, if we will indent something, its penetration depth will be less. And what do you understand by opposite of this? Softness, that if we indent any indenter on the material, the depth of penetration will be higher, right? So similarly, we can take the analogy for wear also. If indentation is less, then is that material is less prone to wear, okay. So and if the material is less hard, that material is going to, or that material is prone to wear. So if hardness is very high, then these steels have exceptional wear resistance property, wear resistant properties, okay. So now let's try to explore the industrial applications for these three class of steels, okay. Now can you tell me, if we want, which material you want that it should be wear exceptionally wear resistant? Think of any engineering applications, okay. So the first application which will come into your mind, it may be uh, uh, what files which you have used in your mechanical workshops, or milling cutters, okay, and drills. So we want that these tools should not get deteriorated, and so that we want that it should have exceptional wear resistance property. So these engineering products are manufactured from Eutectoid steel. So drills, okay, and we have ball bearings, okay, and we have punches. You have seen during punching that wear happens. So what we want less wear, then you have to select Hypereutectoid steel, okay, and ball bearing, okay, and another is knife. So these are the engineering applications for Hypereutectoid steel, okay. Now let's explore this Hypoeutectoid steel, right? In Hypoeutectoid steel, you can see that strength is low to medium, but its toughness is very high. Okay. So these Hypoeutectoid steel is very useful for structural application. So what are the structural applications which you have seen? Okay, so if you have visited to Nagpur railway station, so there you will get wires, some bridges, that wires are there. So these are used in bridges, okay, in wires, and it is also used in car body panels and in ship hull, ship hull, it should have high toughness, okay, and structural I section beam and pipelines for water oil transportation. Okay, so these are the applications for hypoeutectoid steel. Okay, now let's come to eutectoid steel. Okay, so in eutectoid steel, its strength is high. Right? Now think of any applications which have high strength, okay, and it have moderate toughness, and hardness is high. What does it means? That it have good wear resistance property, good wear resistant property. Right? Now let's think of these applications. So we will get music wires, we will get it, uh, music wire and springs. So in spring, what we want, that it should have high compression strength, and with this compression strength it should have a moderate toughness, that it should recover its shape easily, okay, and hammerhead railway track, and cutting tools, when the cutting tools, or when it get heat treated, then only we can use for cutting tools. So I hope uh, these are the potential engineering applications for different kind of hypoeutectoid steel, eutectoid steel, and hypereutectoid steel. Okay, but before using these steels, we have to do its heat treatment. Okay, so we will explore this section in further lectures. Okay, so this is all for today.